Hi, so this is James Dooley, uh, here giving my presentation on the use of transformer networks in classifying radars. Um, so the problem, kind of to set the stage, I was really interested in kind of looking at the measurements that a typical radar warning receiver would receive over the course of one sampling of a radar in the wild, and then trying to build a classifier out of that, and kind of seeing what the viability of using transformer networks are for performing that task, basically. So radar warning receivers, RWRs, you know, they're frequently used in fighter jets and in wide bodies, and there's even some ground-based radar warning receivers. And they passively collect signals from the environment and then inform the user of kind of what's out there. Usually they'll give an assessment of um, what radars are active in the environment and what mode of operation they're in, as well as whether or not, potentially you are the target of said radars or if they have sight on you, right? Um, and the three big things that an RWR is going to measure is the frequency, the pulse duration, and the pulse repetition interval, um, which is the amount of time from leading edge to leading edge of two pulses. And I have a nice little graphic here. Uh, so here the blue colored in spot would be the measurement of pulse duration. So basically, you're just your time on, right? And then for PRI, it's the time between the two leading edges. All right. So a radar in time. So the radars themselves aren't simply fixed to one set of these parameters. They don't just operate on one frequency or one PRI for any given length of time. So any radar that has a somewhat complex task, um, like a search radar, or say a coastal defense radar somewhere, is going to be doing something more than just uh, sitting still, only using one pulse repetition interval or one frequency, right? And so common PRI types that we'll see in the wild, obviously stable, meaning the PRI is unchanged over the course of its operation, or in this case, it's stable over the course of one sampling. A dwell-in switch, meaning that the radar is um, changing its PRI every so often, and then a stagger, meaning that it's a repeating pattern of PRIs. So in this case, like saying 10 microseconds, then 25 microseconds, and then 33 microseconds between the leading edges of two pulses, and then repeating that pattern. And then we have agile slash random, in which case a radar is actually just uh, choosing a PRI at random from within its operational limits, and then it's changing that between every pulse. And for radar frequency, or RF, um, you're basically seeing all those same types as we saw with PRI. So stable, dwell and switch, random agile, or patterned agility. And then for pulse duration, they can change as well. It's far less common to see that. Much more commonly, pulse durations are just fixed, or if they are going to be changing, then they're going to be duty cycle dependent, meaning they'll keep a fixed duty cycle of like 10%, and they would always deviate by that amount as the PRI changed. So that's kind of the setup for what we would expect to see, and in a common in the RWRs that exist today, those sorts of features would be manually programmed and then derived, after taking those measurements and then looking at the radar over a certain amount of time. They would attempt to derive these features. Um, And the real problem is data. So we can't actually, we don't have any publicly available data sets to try and look at these sorts of things. So in order to get around that, to test the viability of a transformer network on identifying radars, then we need to build our own data sets. And the first thing we need in order to do that is going to be an emitter generator, right? So we have to have some way of creating basically a fake radar that we can then sample and then use those samples to build a data set. So the ground rules for these emitter generators, we're going to set some limits on RF and the PRI and the PD, trying to kind of constrain the scope of the problem. And then we can generate emitters to classify. So for frequency, these are going to be limited to between 200 megahertz and 10 gigahertz, with bandwidth between 200 meg and 1 gig. The min channel spacing, so the min distance between two channels of operation, is going to be between 3 megahertz and 23 megahertz. And the possible RF types that we have are going to be stable. So it could be a fixed frequency for an entire sample. Dwell-in switch, meaning that it changes RFs after every 5 pulses. And a pulse-to-pulse agile mode, meaning that it changes RF every single pulse. And next, we have the pulse repetition interval. So our PRI limits are going to be between 10 microseconds and 4 milliseconds. Every PRI also has what's called a quantization. So this is similar to the channel spacing for RF, but it's basically the smallest unit of time that the PRI can change by. Almost as if you had a background clock that it was keeping to. And so the smallest delta we can have is either 1 microsecond up to 7 microseconds. And then the possible PRI types are the same as for RF. So we have a stable, dwell, and switch in the full agile, with the one addition being the staggered PRI, meaning you can still see the sequence. And in our particular case, the staggers can be between 3 and 6 elements. So there's some variation there. And one of the important things to note for both PRI and RF, the reason I picked those particular limits is because the max is multiple orders of magnitude larger than the min, so you're seeing variations similar to what you would see in a real radar, right? And then for pulse duration, because it's so highly correlated with PRI, you're going to see, pulse durations that are much more common towards the lower end of the limit. But the absolute pulse duration limits are between 1 microsecond on the low end, or the minimum of either 400 microseconds or 1/2 of the smallest PRI for a given emitter. And PD types can either be fixed or duty cycle driven. So those are the only two that you're going to see. So sample generation. So after an emitter is created, there's a sample generation function. And when that occurs, then the RF, the PRI, and the PD class will each generate a list of 20 points, basically. So you'll generate 20 PRIs, 20 RFs, and 20 PDs. And they're all generated for PRI and RF. These are generated independently of each other. And then for the PDs, they take the PRI as an input. So in the case of a duty cycle dependent pulse duration, it'll generate accurate PDs for the emitter. And then additionally, after that list of PRIs and RFs and pulse durations is generated, each emitter has a sampling error that's defined by sigma. And so when each emitter is created, its sigma is randomly picked as a value between 0.1 and 0.3. And the reason for this is just to give an additional, for me, was to give an additional hidden variable that the neural net could learn. And this is something else that you'll see in real radars. They frequently operate in suboptimal conditions, really dry deserts, really hot places, really warm places, really cold places, or they see extreme temperature variance, and this can have an effect on the accuracy of the timing mechanisms. And so you'll frequently see a dithering both in frequency and the clocks that generate the PRIs. And so it's very common that you'll see, um, you know, radars that become less and less accurate over time. Just like any other electronics, it's kind of left out in the elements. And then for our purposes, each emitter has its sample. Each emitter sample has its values normalized to between 0 and 255, and this creates a 3 pixel by 20 pixel grayscale image. So in case you're wondering why, the reason for this is that I took the vision transformer um, straight from. Actually, let's go to the next slide here. Um, so the network that I chose to use was a very scaled down version of the vision transformer described in An Image is Worth 16 by 16 words. And in Keras, the patch encoder really wants a 3-channel RGB image. And so the easiest way to do that was to simply take my output of a matrix or an array and turn that into a grayscale image so that the baked in patch creating neural network layer in Keras could simply take my matrix as an input and I could use its patch encoder without having to build one myself. So that's the reason for that decision. So anyway, every sample from my from an emitter that gets made is turned into one of these images, and then there down below you can see the patches that get created that are ultimately fed into this transformer encoder. All right, so the model specifics. So this particular model, the input patches are 5 pixels by 5 pixels. So this ultimately leads to 16 patches total being created for each sample. And the model uses 5 multi-head self-attention blocks, as described in the paper above. An image is worth 16 by 16 words. And this is followed up by a 2-layer feed-forward, fully connected neural network, and then the final classification layer. So one of the advantages of generating our own data is that it's really easy to do experiments with, to kind of judge the performance of the transformer network. So I set about doing 4 experiments. The first experiment, we generate 10 sets of emitters. Each emitter set, which each one of these eventually becomes a data set. So each emitter set contains 400 emitters. Each emitter then generates 750 samples. So, for instance, if an emitter had a full gig of bandwidth and it had a channelization, a min channelization of 3 megahertz, it would be possible, for each frequency to be sampled twice, for instance, if it was a fixed frequency. But it's definitely possible to have frequencies that wouldn't have necessarily been sampled, given this schema. It's possible that some things could have been missed. In addition, after these samples are generated, there's a training and validation set are created, and we have an 80-20 split between training and validation. And then 20 additional samples are generated that are set aside solely for the test set. This experiment is run a total of 10 times, on those 10 sets of emitters that are generated. And then after that, we accumulate results for accuracy and such. So experiment number 2 is the twins experiment. I was particularly interested in trying to make a determination as to whether or not the transformer network was learning the time variant properties of these emitters. So basically, could it tell apart the different ways that emitters were changing in time and, still be able to accurately classify them in that way. And so in order to do that, I had 100 emitters generated, and then for each emitter that was generated, a twin was also generated that was identical in every way parametrically. The only difference was that either the RF type or the PRI type for that given emitter was randomly selected to be something different, right? So in that way, if we have a high level of accuracy in experiment 2, then we know that the transformer network is indeed learning these time variant features of the emitter. And so leads us into experiment 3, which is the pulse drop experiment. So one of the big things that drew me to trying to use the transformer networks was in natural language processing was their ability to impute missing data and still come up with an assessment, of the sentiment, for like a tweet or something. And so I wanted to see how well these networks impute missing data, say if we had a bad pulse measurement taken. So in experiment 3, all the conditions are the same as in experiment 1, except for this case, in the test set only that is generated, each sample has one pulse that gets dropped, right? So in effect, if you were to have a pulse train of 20 pulses, it's as if one of those pulses just didn't get measured, right? The net effect of this is that one of your PRIs is going to be mismeasured, potentially twice as large as it should be. And you'll also be losing that frequency and pulse duration data that was associated with that one pulse. And then finally, we have experiment 4, which is pulse drop 2. And this is all the conditions are the same as in experiment 3. But in this case, both the training and test sets have dropped pulses. So in this case, the transformer network is being trained with dropped pulses. And so, to make a determination as to whether or not the network needs to see this in training in order for it to be able to manage, seeing that in test. All right, so one last thing is a fun metric for the data sets that were generated. So every time a data set was generated, I looked at each emitter's coverage over the PRI and RF and calculated basically an area for what portion each emitter covered parametrically, or basically if you took the sum total of area covered by all emitters, how many times over would they cover the frequency in PRI space? And then that became the area statistic. I didn't incorporate pulse duration into this because pulse duration was so highly correlated to PRI that I didn't think that it would make it a useful metric to look at the total volume covering all 3 parameters. But it does allow you to see just how much parametrically how much each data set covered the RF and PRI space. And you can see that for almost everyone, they hover around 1.75, almost covering the entire parametric space twice over. So just something interesting about the data sets to kind of show how densely packed in there they are. And so here's the test results for the experiments. So kind of looking at the first test, the normal test, on the training side, you can see Really for all three, they're all kind of hovering around, between 96 and 98%. The only one that deviates from that too much is the twins data set, which kind of floats between zero point 0.9 and 98%. And then on the test accuracy, um, kind of one of the big takeaways here is that the original pulse drop experiment, um, which only had pulse drop in the test set, has terrible performance. I actually had to truncate the graph to start at 0.75. It actually goes all the way down to only 50% accuracy for that test set. So basically, if the pulse drop is not included in the training set, then it has terrible performance. It has no idea how to handle that when it sees it in test for the first time. But you can see from the pulse drop 2 experiment, if that pulse drop data is included, or that pulse drop sampling error is included in the training set, then the network's very capable when it comes to handling such a thing. And we have some conclusions. So obviously for experiment 1, the normal had good overall accuracy between 96 and 98%. For training, even higher in the test set. The twins experiment had less reliable results, kind of a larger spread, as shown by the violin chart. But it did show that the transformer network was learning to differentiate between the time variant parameters for the emitters, which was one of the things I wasn't surprised about, but I definitely had a sigh of relief when I first saw that experiment went through and worked, and that it wasn't simply keying off of the measured parametrics. The pulse drop experiment, experiment 3, was the one I was kind of most surprised by. The fact that there was such a severe drop in performance when seeing the test results versus training, because there was such a huge difference. My best guess there is that stable PRI types, seeing such a severe change in PRI and what it was previously considered to be a stable PRI, I'm assuming threw off that filter in the network, causing it to pick one of the more agile emitters that was nearby parametrically. And then, of course, Pulse Drop 2 showed that once you had any kind, they could see that error in the training set, that it had performance results that were pretty much on par with Experiment 1. So that's the end for the PowerPoint. So I'm going to switch over to my collab. So all right, so I wrote all my code in Colab on Google. It was convenient because I could simply run on one of their GPU runtimes and not have to burden my desktop computer, and also I could kind of work between my desktop and my laptop real easy. So all my code's hosted there. Here you can just see some real boilerplate, import statements, all that stuff. This here just mounts my Google Drive, so all my experiment results are actually hosted on my Google Drive, and then at the end of every experiment run, it all gets saved off on the Google Drive. So if for some reason I got kicked off of my Colab instance, I wouldn't lose any data. Nothing went to waste. I didn't actually generate any of my plots in Colab because they look terrible. I actually generated them all on my personal computer because I could use a different output engine for Matplotlib, but they're there to look at if you want to. And here's the real meat of it. So this is the start of the definition for my classes that actually generate the data. So you can see here the PRI class definition. You can see there on the init, I can kind of override all of the basic properties for each class. if I want to, but in reality, I never actually use that. And you can see here, we start off with the beam width, or I reuse the bandwidth from the RF class. But basically, you're choosing between 200, 500, or 1,000 microseconds for the range between the min and max PRIs that it can choose. And here, you define things like stagger length and the Q value, or kind of the clock cycle delta there for the PRI class. And then kind of scrolling down, you can see the generation types. So this is the gen sample function here. And this is basically how all the different PRI types have their samples generated when asked by the emitter class. Kind of all the same parts here for the pulse duration class. Pick your mins and maxes. Although the max pulse duration is a function of the minimum PRI that gets passed to it, so PD has to be created after the PRI gets initiated. And same thing, you can see the gen sample functions there. And then RF, very similar to PRI in its structure, where you get your channel widths are defined there. And you see everything too uses the random class to choose between a list of things, right? And so you can see here the beam width is either a choice between 200, 500, or 1 megahertz. And then, choosing the min and max values. And then here we have the gen sample function for generating the list of 20 RFs. And then here we have the emitter class, which actually puts it all together, generates our RFs and our PRIs, our PDs. And then we have two sample generation methods, one for generating the pulse drop sample. So it basically generates the same code, generates a sample, and then it randomly pulls one pulse out and then changes the resulting sample to account for that loss. And then just your standard gen sample. One thing to note here too is the return statement looks really funky, and that's just because I am actually returning essentially a 3-channel RGB image from the gen sample function. And so here I can make sure my sample generation works, and there you can see an output array which is sampling one emitter. This code here just generates a list of 400 emitters. And that's only so... Oh, my bad. So this is actually definitions for the gen emit list. So at some point I had to turn all of these cells into actual functions so my experiment could run. So initially these would just run by themselves in order. This here just exists so that later when I do the data augmentation for the neural network, it has a sample data set to use for the normalization layer. And that one normalization layer gets used for every data set that gets generated after, but obviously they're good enough. And this will take a couple minutes to run. So I will pause while this runs. All right, so that's done. I have our 400 emitters here. You can see this is basically all of the parameters for defining the transformer network, as well as some of our things like learning rate and weight decay for the optimizer, and the batch size for some of our training settings and things like that. So obviously this is required. A couple important things here. We define the number of heads on the output of the multi-head attention block, as well as the projection dimension for the multi-head attention block. So we have, and then also the MLP head units defines the number of neurons in the fully connected layer after the multi-head attention block. So some really important things get defined here in this spot. This is our data augmentation. So um, all I'm really doing here is just normalizing and then resizing the data, so nothing terribly important happens right here. But it'll still take a minute to run either way. All right. And so now we're just kind of defining all of the functions here, and this is nice. You can see a sample from an emitter. Um, and so just by looking at it, I can already tell that the pulse duration is actually duty cycle dependent because you can kind of see it changing there. And, I can sit here and regenerate, multiple samples and kind of see what they look like. Obviously, for a lot of these, you're going to be able to delineate them just parametrically based on the differences in RF, PD, and PRI. But obviously, since we have 400 in a relatively small space parametrically, um, the transformer network will have to learn some of the time variant features in order to actually separate these classes. All right, so we have our patch encoder, our classifier. Oh, so one thing I forgot to mention real quick before I get too far, and go over this sigma value here. So every emitter has a sigma value that's generated for it. And then when a sample is actually taken, it has this um, it has a Gaussian noise applied on top of every output. So you can see here in this pulse-to-pulse agile sample generated, I have the normal random.normal, and then the scale equals the sigma. And that's applied on top of every single sample that's generated. And this actually becomes basically another hidden variable for the transformer network to learn, is essentially, each emitter should also have a noise level essentially um, that should potentially be learnable. So even if something that's fixed will have some deviation across its RF or NPD and PRI, as that same sigma value is used across all three parametrics. So yeah, even if this was a completely fixed RF and PD and PRI, you would still see some striation in the output. All right, so didn't really touch on this. So this is the classifier section. You can see here we have our inputs, which is literally just the input shape, which we defined earlier, which is a 20 by 3 by 3. We have our data augmentation layer, which is just normalization and resizing from a 20 by 3 to a 20 by 20 image. Here we have our patch encoder. Here we take on line 8, we take our encoded patches, and then we pass it into this for loop here, which creates our 5 multi-head attention, or not multi-head attention blocks, but the 5 transformer blocks, which has 5 multi-head attention layers in it. So first we do our normalization. We create our multi-head attention blocks with the number of heads and the projection dimension there. We add in a skip layer from the encoded patches line to the attention output. We normalize again, do our multi-layer perceptron, the MLP output, and then we have another skip connection from X2 to X3, or and X3. Do that 5 times. Then we have a normalization layer, we flatten, and then we do a dropout. And that's pretty much it. for our classifier. This is actually my first time using Keras. I've previously only used PyTorch, so I was really impressed by how easy it was to get all this working. So this is our run experiment. So we define our optimizer and our model. Um, and this is kind of all boilerplate code that I got from the Keras tutorial page on their website. So this was pretty easy to use. And the two main things that I do use is the accuracy, and then I specifically set up a sparse K or sparse top K categorical accuracy to take the top three. Um, Oftentimes in radar warning receivers, they relate more than just the first ID that they have. They'll usually relate two through what's called mippling, where it'll oscillate between multiple symbols or kind of have like it's somewhere on the display where you can tell the user, hey, I think you may have at least one of two or three different things. And so it was important for me to kind of see not just how accurate, the number one guess was, but to see how accurate the top two or top three guesses were. And routinely on all the models, I know it wasn't in my violin chart, but they were near 100% for top three accuracy, which I thought was pretty good. And then, so there's our history definitions and yada, yada, yada. And then, so this is where the actual experiments are run. So you can see kind of the order of operations. This is for the normal experiment. First, we generate an emit list in an area. So after generating our emitter list, we take the number of classes. We set up our X train, Y train, X test, and Y test. Define our input shape. Create our classifier, and then run our experiment. And then after that, we get our accuracy and the top three accuracy from the history. All of this is turned into a pandas data frame, which is then concatenated with the experiments data frame. And then you can see here, this is saved off to my Google Drive. So I'll run this for a second, just to kind of show it running, but it's going to take a minute, so I'll probably cut it off after that. So we finally got it running. I'm just going to show a few epics training. It takes about 30 seconds per epic. One of the things I was really impressed by, I guess, is how quickly the accuracy comes up in these tests, and it converges on it gets to within 80 or 90% accuracy within 10 epics usually, and then comes up considerably, in those last 20 epics, usually getting up to like 95 to 98%. And you can see here after one epic, we're already above 80% accuracy on training. So overall, I was pretty pleased with the performance of the Transformer network. And that's about all she wrote. So thank you very much.